And so everything you see in press conferences tends to be stuff that works beautifully, or maybe works for the wrong reasons, but still works. And there's lots of stuff that never make it into the press conference. And so there's a few examples here from Mars Pathfinder, but Dr. Stern, who probably spent an entire day on this subject, much to the delight of his colleagues now. But anyway, one of the things you get for buying a launcher back in the old days, I don't know if they do it now, but this is back when there was a McDonnell Douglas, and so we spent $70 million and got a Delta, and they printed us up T-shirts as a result. And so you got T-shirts with this logo, which I thought was pretty cool. So you get something for your $70 million besides just a big candle at night. Thanks. And of course, I was on Pathfinder. Pathfinder was essentially a way to deliver a rover to the surface using airbags. And the rover rode for about 78 days before the battery gave out. And it was very successful. And did a lot of cute things. We named rocks. And the rover chief, Donna Shirley, was always referring to the rover as her. And that's very cute. Next slide. The first thing you find out is that having airbags is good and bad. Airbags is a great way to land on an unknown planet where you don't know precisely to the meter where you're going to land, so you can't necessarily choose a soft spot. But the airbags are made with 3-ply Kevlar. And so you can wrap yourself in that and be relatively invulnerable. And the problem is that once you deflate the airbags, you're actually sitting on about 2 feet of airbags. So you're way up high off the ground. And we sort of expected, because this is the camera here that I work with, we expected to be about 5 feet off the ground, about this high. Instead, so we called that one mic car unit after a, Kelly knows what I'm talking about, after a noted Mars scientist. But unfortunately, well, and then much to our surprise and glee, we were actually 6 feet 9 inches off the ground. We were one Michael Jordan unit. So, next slide. The very first thing we did was we took this grand panorama and then we sent it off to the President of the United States. And in this grand panorama, you can see the rover has moved up, and it's a very agile thing. And so it essentially worked its way up this big rock. And if you're talking about the Sojourner rover as a little dog, I suggested to Donna Shirley that this was evidence that the Sojourner was not a girl. She did not take this in the spirit that I intended. What she did was she made us go back the next day and retake this whole section after we maneuvered the rover off the rock. And then we released that. And you know, for good reasons. Next slide. We had planned to have a great public information office release of Earthrise over Mars. Earth is right there. What we did was we discovered that in the early morning, you get a cloud layer on Mars. Nobody knew about that. But of course, we tried several times, and every time we tried to take Earthrise at dawn and have a wonderful press release, bloody clouds were in the way. Of course, this was very good science, and what happened was that the next press conference, we announced that we had discovered early morning clouds on Mars. It's not like we thought to look. Next slide. This is a little bit of a makeover. We built this camera. I'm partially responsible because I was the project manager. It works really, really good. But it always had a pointing offset. And we would adjust for this pointing offset. And the pointing offset would change. And so one of the things we did was we had to save bits. We had little subframes where the idea was you'd take a picture of a rock and do spectroscopy on it. And it would be a little box, 64 by 64 pixels. And so you had to have good pointing. And all the X's are where we were actually pointing. Right there, 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 there. And all the boxes are where the box actually ended up. And what really helped wasn't there were lots of rocks on Mars. So whenever we had a box, there was always a rock in the box. It just wasn't the rock we were aiming at. I don't know what happened to this one. Next. We had some solar filters so we could take pictures of the sun through the Martian atmosphere and characterize the atmosphere. These were 1,001 neutral density filters, so you'd only get one photon for every 1,000 or so that you filter, in order to avoid damage to the camera. What this is a picture of the sun through one of the regular filters. One of the co-investigators was trying to image the anti-sun hemisphere and couldn't get his sun straight, so he made a 90-degree pointing arrow. So instead of pointing at 90 degrees anti-sun, he pointed it straight at the sun. You get pointing arrows.
Did it damage anything?
Well, actually, go back. What this shows is that we have gates. I'm blanking on the term, but the CCD actually had a fail-safe mechanism. If the wells got too full, it would bleed off into ground, and so it wouldn't damage anything. Of course, this is against the flight rules, and you lose your privilege of writing commands when you do that. Next. This is one of my favorite pictures. This is a picture of the rock garden at midnight. What we're trying to do is take pictures of Martian Phobos. This one was supposed to be Phobos, but the problem was instead of pointing down, the camera pointing up, the camera pointed down. We couldn't figure this out, so we asked the spacecraft engineers, and we had to drive this by the timing in the spacecraft computer. And up-down, spacecrafts don't have up-down, they have positive Z and negative Z. And it turned out that it was easier for the guys building the spacecraft to have positive Z pointing out the bottom of the spacecraft. That's the origin. Pardon me? The origin was actually on the base of the flight path. Yeah. Well, it made perfect sense for an engineer. It was just that we didn't get that memo that positive Z is down on Mars. And so for the first couple of times, we pointed down. And then we figured this out, pointed up. So if you want to know about the term here is quaternion. If you want to know about spacecraft quaternions in mind-numbing detail, again, ask Dr. Stern. He can tell you all about spacecraft quaternions. Next slide. See, we did actually get Phobos and Deimos. So we figured this out. Next.
I can try to make it interesting.
It is fascinating in many ways. It's again, a part of the full range of human peculiarities. And remember, you try to do things that are easier, and quite often it's easier to have positive Z out the bottom of the spacecraft. So dust devils. Turns out, dust devils are probably the most current active process on Mars. When we took this presidential pan that included the rover lifting its leg on the big rock, we got 3 dust devils in the distance. Here's 2 of them. And the spacecraft, which occupied about yay much space on Mars, on average, got hit by a couple of dust devils every day. And nobody expected this. In fact, we got a participating scientist proposal from a guy who said, I don't need anything you're not already doing with the spacecraft. All I'll do is take a look at all the pictures that you produce that have the horizon, and I'll check them for dust devils. So you don't need to take any additional data in order to satisfy my requirement. We all looked at this. I was on the review board. He said, ah, never happened. There aren't that many dust devils on Mars. Ha! And of course, when we published the presidential cam, we put it out as a press release with with the digital data. What he did was he downloaded that, and the next day came out with a press release that he discovered 3 dust devils on Mars. Because they were there. We hadn't even noticed them. And so he was absolutely right and we were wrong. Next. This is just what a dust devil looks in atmospheric pressure. There's 2 on that day. There's another one over there. I was thinking, this must be really an amazing dust devil place, because I've lived in Tucson all my life, and people who've lived in Denver probably know this. You see dust devils all the time. But how often do you get hit by them? And I was thinking that and walking to lunch, and lo and behold, one of them came out. I thought, okay, that solves that problem. But how much time do you actually spend in parking lots and wandering around and not quite as? Anyway, next slide. One of the problems with having a rover is this is the early days of the rover program. So they had 3 rover drivers, but they had like 12 professional warriors. So you want them to do something, because it was carrying these scientific instruments. I want you to go over to this rock. And then the drivers would say, no problem. And the warriors say, oh, I don't know about that. This will require complex maneuvering. Yeah, terrible things. So it turns out that, well, the problem was that it was actually afraid of its own shadow. Because what it does is it has some smarts to avoid dangerous things. Well, dangerous things cast shadows. Pits cast shadows, big rocks cast shadows. And since it also cast a shadow, you really couldn't maneuver before 10 in the morning or 2 in the afternoon local time. Because if it saw its own shadow, it would stop. It was also actually a very good climber. And so you had to worry about it climbing itself into a difficult situation. And of course, it could, like any vehicle, it could high end itself. And so to get anything out, it required planning, decision making, essentially a round-the-clock effort to sequence what you wanted to do and get it done. And of course, this had to be done several days in advance. And quite often, by the time you saw the results of your clever maneuvers, things had radically changed. Next slide. Like that. We didn't really need for that. Next slide. So, just to leave you, one of the things that the public noted most about Pathfinder was we had these cute little rock names that tended to be cartoon characters. Actually, the science team had not thought this through before we got to Mars. Because the idea of pointing the camera at specific rocks, it quickly became apparent that trying to use some sort of a grid system was completely unusable, because you could never remember the grid coordinates of the rock that you wanted. So we started using nicknames. Now, normally you would think that this is a clever thing that NASA's doing for PR, but I will give you this one piece of evidence. The names were easy to use, and therefore NASA had nothing to do with the choice of names. I actually set out some naming standards. The names had to be easy to remember, not snide, derogatory, or a proper name. You can't name these things after your children. And I'm a terrible speller. I had to be able to spell it on the first try, otherwise we reject it. And so that's why we ended up with cartoon characters like Scooby-Doo. Actually, it was my 7-year-old son that suggested Scooby-Doo. I slid a couple of things in that are actually violations of my own rules. My uncle had 6 brothers. They all had kind of snide nicknames. And so there's a Spud Rock after my number 3 uncle. There's a Gallstone Rock after my neighbor who had a gallbladder out. Things like that. So anyway, I think that's the last slide. Any questions on the human frailties of missions? Yeah.
I saw Donna Shirley on TV explaining the mission quite a bit, and I just wondered, did you see the result of all of that publicity, getting more and more support for the mission?
Oh yeah, I think that the outpouring of interest from the general public just left the NASA administrators speechless. It was jaw-dropping. They had no idea that people were that interested in Mars. That kind of public interest really created the subsequent Mars program as we know it today. Because they just didn't believe it was there, and they were very surprised. Yeah.
I know I've heard references to this, but has there ever been a microphone, or at least serious discussion of putting a microphone on a lander?
Oh yeah.
And has that happened? Will it happen?
There was
It
one
did.
on
Mars
the
Polar Lander.
Mars Polar Lander.
Yeah, Mars Polar Crasher.
And there was one on a French mission that never launched.
And I think there was one on the British mission, so maybe.
So there hasn't been a
Microphones are the
success.
source of crash.
There hasn't been a
So
successful.
don't put a microphone on your lander.
Yeah. Not that I'm superstitious.
Would there be any science to that, or would it be like, I think it's an amazing outreach thing. I mean, the idea of like tuning in and being able to listen, I think is powerful, but is there any science reason for it?
Not really. Wind whistling. Actually, one of the things I didn't put in here was the checkered past of wind instruments on Mars landers. Because people try and they mostly never work. But that's another story.
Of what instruments?
Wind instruments, trying to do wind velocity. And the problem, of course, is that wind velocity is not that big of a scientific interest. You really want to know atmospheric pressure, and we do that really well. But wind velocity is actually kind of tough if you don't want to use moving parts. And moving parts are just the kiss of death in the spacecraft, especially in a coastal environment. So they cost a lot of money, and the missions are all cost constrained, so they don't want to pony up a lot of money for a wind experiment. That's another whole strange subject.
Since you were talking about dust devils, I heard a strange fact a while back that the Mars rover missions were kind of scared of the dust devils, possibly damaging the solar panels, stuff like that.
Oh,
but as
heavens.
it turned
No,
out, it was
actually-
actually good.
Yes,
because
actually,
it cleared off the dust.
Yeah, they seek out dust devils because as much as you can.
Yeah.
But
Wasn't
they
sure
love
if that
dust
was
devils
true or.
because what happens is that Mars is a dusty place. Dust will degrade the performance of your solar panels. So any way you can get these things cleaned off, so much the better.
Would an astronaut on Mars, I've had a dust devil go through me once too, it was quite thrilling. But
Yeah, it's actually kind of a disorienting experience.
a little bit, yeah, it's very brief, but would an astronaut, given the lower pressure and thinness of the atmosphere, would it move you around? What you see?
Probably not.
Would you barely notice the dust devil going by?
Well, you would notice all this dust.
Dust, but I mean, as far as there'd be a little air pressure, right?
Well, you're not subjected to the air pressure anyway, otherwise you'd be dead. So you're not going to sense it yourself.
Relative change.
I'm just saying, the feeling of force.
Yeah, probably not much.
I read somewhere that it would be like someone lightly moving on
Oh.
that deep. But as a camera operator, do you have to live on a solar cycle?
Yeah. How was that? It makes you weird over time. Also, it makes you realize that that's how I got where I am today. Also, you find out that the distribution of 24-hour places to eat in that part of Pasadena is pathetic. And then to get 24-hour service, you have to go to places that you'd probably rather not go to. But, you know, what the hell.
You're also playing on Mars. So
Yeah, I know. We're playing on Mars. Anyway, go ahead.
So the rock nicknames and things like that, have those lessons learned been incorporated in Curiosity and
All of these guys,
places been
all of these, there's now NASA directives on nicknames.
so the names have all been run through committees and approved.
Oh, yeah, they do that now. Yeah, we got away with this, but the way you name a rock is you put a name on a yellow sticky, stick it on the panorama. There it is, unless somebody objected to it, where they take the yellow sticky off. And so rocks were, you know, consensus. Yeah.
All right, now I need to find out something I've wondered about for quite a long time. I need to set the stage for everybody. This panorama that he was talking about was at the back of the auditorium at the Jet Propulsion Operator. It's a giant panorama, maybe 20 feet long,
30 feet long.
30 feet long, and true to what he said, as they named these rocks, they'd get a yellow post-it, put the name on it, and like put it on the rock.
Yeah.
A few of us were sitting in the auditorium one night, and we were bored out of our skull, and we had noticed this yogi, you know, this sort of cartoon character thing. So we thought of every cartoon character we could, found a pad of yellow Post-its, and named all the rocks that we could. Did any of those stick, so to speak?
Well, probably they did. You see, anybody could do this, and the only editorial comment was if somebody came along and decided that I don't like that name. And so, probably. I know that the 4 or 5 that I named stuck, mostly because I would come by, if somebody pulled it off, I would come by.
Like Tweedledee and Tweedledum and
Tweedledee and Tweedledum did stick. Yeah.
A lot of the dust devils in Gusev crater were, I guess, fairly small, but what about the ones that are over 20 kilometers? Would you completely avoid them? How strong?
Well, you can't avoid them because they come and they go fairly fast. You just get hit by them. Well, if there's enough of them. But I think dust devils, like anything else, have a range of sizes. The small ones are far more numerous than the big ones.
You're talking about the ones that were photographed from orbit?
Right. In Amazon or
The ones that are sort of getting to almost hurricane force or tornado force. Yeah. I don't know. I should get to Phobos and Deimos. So, shall we do that? Yes. Okay. So, moons of Mars, very interesting places. Phobos and Deimos, Fair Dread, next. These guys are relatively close in. About 3 Mars radii out for Phobos and about 7 Mars radii from Deimos. Now, the way it works is the tidal forces, if you're inside the Mars synchronous rotation, where you'd be matching the rotation of the planet with your own orbit. If you're inside Mars synchronous, tidal forces will actually decay the orbit. It will take orbital energy out of your orbit and add it to the rotation of Mars, and that's what's happening to Deimos. Or Phobos, excuse me. And then Deimos is reversed. You're getting tidal energy put into the Deimos orbit, so it's actually increasing, but only slightly. And these things are small. Deimos is 6 kilometers. Phobos is about 23. They're dark. Albedo is around 7%. Now, 7% is a little brighter than copy machine toner, but not a lot. And they're low density. 1.87 grams per cubic centimeter. If you live in some place that is not constantly baked, like Denver, and you pick up a dirt clod, a loosely aggregated dirt clod is about 1.8. So Deimos is a little low for a dirt clod. Phobos is about a dirt clod density. Next slide. So they're both small and dark. They're both low density. Both have trivial surface gravity. They're both black. They're both about dirt clods, so they suggest that there's lots of empty space on the order of 30 to 40% in these objects. They're both tidally locked with Mars, so they're always going to present the same side Mars. What's interesting is that they're far enough inside the Mars gravity well that for a small body they're in a unique position. Stuff that gets knocked off of Phobos and Deimos is going to reaccumulate in Phobos and Deimos unless it's ejected with enough velocity to escape the Mars system. Because what will happen is that tidal forces and also things like Poynting-Robertson drag and other cosmic drag forces are going to force things back into the equatorial plane and slowly accumulate them into Mars, and that's where these moons are to sweep things up. So they have a tendency to reaccumulate ejecta, and you look at these bodies, and they are thickly covered with a loose regolith. The major difference between the two is that Phobos is a whole lot rougher than Deimos, and this is actually the correct scale. So these are the relative sizes. And even at this scale, you can see that this guy has a whole lot more roughness, a whole lot more topography than Deimos. Next slide. And so let's look at a few pictures. Phobos, this is the Stickney crater, which is a crater diameter is a big chunk of the diameter of the object. In fact, this is big enough that if Phobos had been a solid object when it hit, it probably would have shattered the whole, it probably would have destroyed the whole object. The nice thing about being very porous is that getting hit by major impacts has about the same effect as hitting a pillow with a baseball bat. You can certainly impart a lot of energy, but you just don't get a very good reaction out of the pillow. What happens is a lot of this energy, instead of shattering things, because everything's already shattered, is you just move stuff around and essentially dissipate that energy by friction. And what happens is it creates a lot of these fracture patterns. Next slide. And you can see they're all over. There's a couple of origins. Not all of these fractures are likely to be produced by the major impacts. There's another story to that. I'll get to it. Next slide. But as you can see, there's lots of them. And there's a lot of topography. That's the North Pole right there. Lots of these grooves, lots of these pits, plenty of craters. Next slide. So this is just the edge of Stickney. You also get large boulders like there. If you stare at these pictures, you can find more boulders. Next slide. Now these grooves and pits. In geology, this is sort of a classic landform, where you open up a fracture and then material drains in along that fracture zone. These things are called grabens. And so you can, if you're interested in grabens, you can go do field work and learn about them in sort of the classic graben terrain. I recommend the Rhine graben. The wine is very good there. And you can see the Rhine graben from a number of really good vineyards. But this is a typical morphology for a graben, and you see the same sort of thing in Phobos. There are alternative explanations. One of the ideas is that this is essentially a crater chain from ejecta coming off of Mars. So the idea would be that some high velocity ejecta is tossed off of Mars, and it intersects with Phobos, and it just sort of bounces along the surface. Yeah.
I'm assuming that that's the that's an optical illusion that looks like a ridge to me, but it is actually a rift valley.
Like this?
No, the picture on the left.
Yeah, that is a rift valley.
Okay, it looks like a ridge from this angle, so I want to make sure that.
Yeah, you need to flip your perspective.
Yeah.
Yeah, but, yeah, I think the problem is the sun is from the right on this side. I can't always get the sun orientation in these pictures. I should actually, for this one, I should just actually flip it. Okay. Anyway, I'll talk more about the various schemes for making Phobos and Deimos in a minute. But just suffice it to say that there are people that don't think that these are gravins with these are called drainage beds. So loose stuff drains down into the cracks that are. Next slide. You get a lot of action on Phobos. So you get this is a classic slope failure in geology. So this scallop of material is falling down into the crater. And this flat-floored crater is at least giving an indication that there's more coherent material farther down. But what we're talking about is at least 200 meters of regolith. Next slide. I like this picture. What's interesting is that you see the fracture patterns here crossing. So you have fracture patterns that are going this way, and then you have another fracture pattern going this way. And you see a couple of distinctive orientations of fracture patterns. People with more patience than I have mapped all these pretty detail. Next slide. And of course, for comparison, Deimos. Deimos is one of the smoothest small bodies in the solar system. Next. This is close up as Viking flew very close. Over 250 meters, you get a few craters, but lots of nice flat terrain. Next slide. One more flat terrain. I could show you another half dozen of these and bore you about flat terrain. When I show this to the engineers, they're very excited. The engineers are very excited about flat terrain. Next slide. The point is that Deimos is very much for a small body, a billiard ball. This is Eros, which is not particularly a rough asteroid. And remember, we landed a spacecraft on Eros. That wasn't even designed to land. And we landed it in this kind of terrain. Next slide. So Deimos is a fairly benign place, low gravitational slopes, not very rough, not lots of ridges, valleys, things like that. Next slide. So how do you get Phobos from Deimos? Well, it's a pity that our dynamicist isn't here, because the problem is that several of the leading theories for creating Phobos and Deimos actually are extremely difficult, if not impossible, to happen dynamic. My own favorite is that it's a captured asteroid. You look at the spectra, the albedo, the density, that's all characteristic of an outer asteroid belt, a D-class asteroid. The idea would be that Jupiter, in its early days, is scattering planetesimals like crazy, and these guys got captured by Mars. Capturing by Mars requires a couple of miracles to happen. So the problem is that you've got too much orbital energy to be captured by Mars permanently. And somehow, when you're inside the Mars Hill sphere, inside the zone of Mars gravitational influence, you have to dump a bunch of gravitational energy somehow. And there are a couple of methods for doing this. One of the ways is you have a collision inside the Hill sphere with something else. Another way is that you're a binary or ternary object. So you have a couple of you have a couple of big companions, and while they're orbiting around each other, they pop in the Hill sphere. You get gravitational inputs from Mars. The other bodies fall off and fly out and transfer over energy to those guys. Something, and then the other one stays in the Mars Hill sphere. Once you're in the Hill sphere, tidal forces can drop you down into the equatorial plane, although that's not trivial. And suffice it to say, a miracle has to happen. Or it could be formed by Mars ejected. This is sort of the leading theory. This theory has gotten a lot of currency in Europe these days. There's a whole bunch of French scientists who are really strongly in favor of this. We regularly call each other names. The evidence here is that although the albedo is low, it's actually on the high end of the asteroids. And it does have shallow absorption features that would be indicative of, potentially indicative stuff that comes off the surface of Mars. So the idea is that during the Mars heavy bombardment, you threw up a whole bunch of ejecta and created a circum-Mars cloud, and it formed just like the Earth's moon formed. The problem, of course, with that is that that also requires a miracle to happen. Because when you launch ejected ballistic trajectories, what happens is it will either leave the surface, which is hyperbolic trajectory, or re-impact the surface. That you need an extra energy input in order to get it into orbit. That's hard to do. The other thing is the albedo is kind of low. Mars material is kind of bright. That's a piece of Mars right there. This is a piece of something that is reminiscent of the D asteroid, Sutter's Mill, which recently fell in California. So it's really hard to mistake that for that in most places. There's another theory that it was formed during the when Mars was forming and had a circum-Mars disk of nebular material, and it just got formed that way. Again, the albedo is probably too low. Also, nobody believes this. So next question. Next slide. So why go? I proposed, made several proposals for sample returns for Phobos, for Deimos sample return mission. And there are a bunch of advantages. It allows you to go to Mars and not have to drop all the way down to the surface. You can operate on bodies that have substantially less energy to get there and get back out. It's a source of potential resources because these low albedo things may be rich in volatiles, may be rich in carbon, and that could be useful for further exploration. You can use this as a base for operations on Mars, so you can support telepresence. Excuse me. Your real big problem in going to Mars is that you're open to space environment, and cosmic rays are nasty. The best way to deal with cosmic rays is to get a whole bunch of mass between you and cosmic rays. Well, if you're on someplace like Deimos, 180 degrees of your exposure to cosmic rays is eliminated right there. And the nice thing is that Mars is right there, and it's going to subtend excuse me, about 40 degrees of the sky just by itself. And so between Mars and Deimos, or Mars and Phobos, you're actually providing a great deal of shielding without even having to dig yourself a structure. The other thing is that these guys have been in Mars orbit for a long time, so stuff that comes off of Mars is going to, some of that's going to bang into Phobos and Deimos. And so you're actually going to be able to get pieces of Mars ejecta in the regolith because it's going to hit there. It can't avoid it. Next slide. The thing is that you have pieces of Mars on Earth. In order order to get to Earth, they have to go by Phobos and Deimos. There's no other way. And so some of that's going to accrete on Phobos and Deimos. The nice thing is that what you've got in the coverage of meteorites from Mars is this huge gap between things that were formed relatively recently, within the last billion years or so, and things that were formed right at the early stage of Martian crustal evolution. The only really ancient sample we have is the infamous ALH 84001. The reason you don't have lots of ancient Martian meteorites, even though there's lots of ancient Martian crust, is the ancient Martian crust is all beat to hell. It's been subjected to impact bombardment for the last 4 billion years, and it's covered by ejecta, and it's covered by subsequent eruptions. And so it's extreme, and also it's been eroded by the warm and wet environments of Mars. So it's pretty weak. It's really not all that accessible on the surface of Mars anymore. And the way you find ancient Martian material is you go to some place that's been storing that without having a lot of other stuff dumped on top of it. And that would be the moons of Mars. Now what you're going to do is you're going to find essentially dust grains of ancient Martian material. You're not going to find big rocks like this in ancient Mars. But what you want from these dust grains is not the ability to throw them at each other. What you want is to determine what the rare earth and trace isotope ratios, trace element isotope ratios are. And that tells you how the Martian crust evolved. And if you get enough of this stuff, you can essentially build up a time series of how the ancient crust evolved, and how you make planets, and how you make planetary crusts. And this is the one place in the solar system you can do that. I think it's pretty neat. The other thing that these guys do is that they trap in impact glass pieces of the Martian atmosphere. See all these little black dots here? That one, that one, that one, that one, that one. All of these are impact glass, which sucked up a little bit of the atmosphere when this guy was ejected from Mars. This is how we know that this type of meteorite comes from Mars, because you can look at that atmosphere and look at the atmosphere from the Viking lander that was measured by the various landers, and it's identical. And this is how in the 1980s that people came to realize that these meteorites came from Mars. That and the fact that their isotopic age dating was fairly recent, so it had to come from the planet. One of the very first times I went to a scientific conference was the 1986 Lunar Planetary Science Conference. And I was sitting listening to this guy talk about how this impact glass contained Martian atmosphere. And you know, there's always a question and answer period. And a guy got up and says, only an idiot would think that meteorites come from Mars. In those words. I thought, you know, the science stuff is not too bad. They call each other names. These conferences. And his point was that he had done modeling of ejecta coming off of Mars, and none of his models could get the ejecta accelerated enough to escape Mars gravity well. We have a saying in geology: if it has happened, it can happen. And the fact that your models can't figure out how it happened is not a problem with reality, it's a problem with your model. The very same guy came back the next year, gave a talk where he said, I've proven that you can have meteorites from Mars. Because what he did was he added another term to his model, and woof, off they come. Anyway. What you do here is you can find samples, these little tiny dust grains that are 4.5 billion years old, that can really give you a better timeline on Martian geological history. Because this really ancient stuff is going to be buried by all the subsequent activity on the surface of the planet. Next slide. So anyway, I'm giving you a picture sample return because I like the subject. But the reason you do sample return is that remote instrumentation is a tough thing to do. The space environment is really nasty. I mean, you spend all this wonderful time and care building these exquisite instruments, and you have to build them tough because the next thing you do is you plop them on top of a spacecraft, a rocket, and you blast them into space and you shake the hell out of them. Then you subject them to vibration, thermal variation, shock, radiation, dust, outgassing, spacecraft outgas. That can be bad for instruments. And so it's hard on the calibration of robotic instruments. Also, spacecraft tend to be very closed systems. You don't get a lot of mass, because remember, you have to pay for every gram you throw up into space. You don't get a lot of power. You don't get a lot of volume. Those are hard. And then, what we're talking about is sample handling. I used to run a mass spectrometer in my sordid youth as an undergraduate. And trying to automate and do remotely the functions of even a badly trained student is incredibly difficult and expensive. Because what you're doing with trying to find isotope ratios is you're essentially picking minute minerals out of this little piece of dust. And that's very difficult in terms of mass, power, and volume to replicate with water. And what you get are orders of magnitude better results in terrestrial laboratories. It really makes it worthwhile to bring them back. The other thing is that if you got the samples back, this has to be repeatable. One of the problems with remote instruments is if you do this measurement and you're worried about the calibration, you don't get a second chance. You're always going to be worried about the calibration. This way you can send it out to labs around the world and people can argue about your lab procedure, but if you got it wrong, the facts is what it is. And really, a lot of the major advances in planetary science are achieved by analyzing these very small amounts of trace elements. What I do is I do bulk properties of meteorites. And so I go to the meteorite curators and I say, you know, give me 100 grams of this meteorite. Well, 100 grams is probably more than they've given out to these isotope geologists in the last 5 years. Okay? And so, next slide. My analogy for this is the Apollo 11 contingency sample. The first thing that, when I was an undergraduate, when I was a freshman in college, I stayed up and watched Neil Armstrong jump down on the surface and kick the dust around. And the very first thing he did was he took out a scoop and scooped up about a kilo of stuff, and he stuffed it in his suit. Because the idea would be that if something happened and you had to leave the lunar surface right away, you'd have something to bring back. And you ask yourself, what would you be able to see in that contingency sample that would impact the science, lunar science? And basically, you would be able to find not everything, but almost everything that you subsequently learned from the entire Apollo program was in the dust in that contingency sample. It was harder to get at than the bigger rocks. But age dating, geochemistry, the existence of the anorthosite, the volatile elements, all these things are in the dust of that contingency sample. Plus you get all the basic geotechnical data about the characteristics of the dust, which they of course found out were not very good for the astronauts. Next one. So, I leave you with the moons and Mars. We should go and get some. Thank you.